Thank you for attending this session on effective tools for requirements and concept development using the SDI Tools Triptych software. In this discussion, we'll be focusing on the design selection tools that are included in this set. The SDI Tools software includes the Triptych tools, which include a suite of tools that are important for requirements and concept development for any product or process development activity. We have previously discussed the use of the affinity diagram techniques, analytical hierarchy process, quality function deployment, FMEA, and the trees technique for developing alternatives. In this discussion, we will focus on the review of design selection techniques such as the Pugh method, the TOPSIS, and the SDI methods for design selection. In our discussions of the Triptych tools, we focused on collecting information to understand the problem, organizing this information, and identifying key needs and wants using affinity diagram techniques. Taking information from the affinity diagram and prioritizing this information using analytical hierarchy process, and then decomposing these needs and wants into general hows or other derived requirements or critical requirements that will be important for developing or designing the final solution. And we've applied quality function deployment techniques for this application. Once we have the general requirements defined, then we can start creating alternatives. And one technique we looked at was the trees method, the theory of inventive problem solving, for coming up with alternatives to conflicting technical requirements that we may have developed. In this area of our discussion, we'll be taking once again a set of criteria which may possibly we can rank order using our AHP technique that was previously discussed, and then looking at how we can evaluate criteria, evaluate this criteria with respect to our various options that are available for a solution, and determine a selection or determine a preferred option using either the Pugh Matrix technique, the TOPSIS technique, or the SDI technique. And then once you've determined your preferred solution, then it may be appropriate also to go back and reassess any risk and do a risk identification using the failure modes and effects analysis technique. So in design selection, the general purpose of this category or this topic is to make a decision that among the various designs or various alternatives or options that are available, which approach most closely meets your various conflicting requirements that you may be dealing with. So there are many different approaches that are available for performing design selection, but generally they have the following characteristics. Number one, you must identify or gather your design options or your alternatives that are candidate solutions for a particular problem. Next, you must identify what are the criteria that are the conditions that these options or this preferred option must meet in order to be selected as the favored candidate. Given that this criteria may not all be equally important to each other, and some may be more important to the stakeholders than others, then we must do a rank ordering and assign an importance value to each design criterion, and then use this rank ordered criteria information along with our identified various options to determine which would be the best approach, and basically do this through some type of a scoring technique where potentially the highest score would be the preferred option. So among the many approaches that are available, we've selected three techniques for implementation in the Triptych tool set. The first is a qualitative selection technique that allows you to evaluate preliminary designs using a Pugh Matrix approach. The next is a quantitative technique, but it is a goal-based technique that can be used that's based on the TOPSIS method. And then finally a purely quantitative selection technique that we've implemented and called the SDI Matrix method. So in the Pugh Matrix technique, it's basically a qualitative selection that you can perform by doing fast qualitative comparisons by comparing an option against a datum or referenced option against each one of your criteria. So it is just a qualitative comparison of comparing, say, a current option with respect to a datum and saying for this option against a particular criteria, is it the same as the datum condition? Is it possibly better than the datum condition, or is it worse than the datum condition? And we'll perform these various very general evaluations and then summarize the information to determine what may be a preferred approach. In the TOPSIS method, which is the technique for order preference by similarity to an ideal solution, well, this is a goal-based decision-making technique. Well, what we will do is evaluate each one of our given options and using quantitative information determine which one may be closest to what we've identified as a goal or the overall preferred option, which may or may not be available. So what we're looking at is which one is, by using the nominal design information, which individual alternative is closest to the ideal solution that we would like to have. And then the SDI method is a quantitative method where we're going to perform our evaluations against our actual design specifications. So for each design specification, you would typically have a target value and possibly a lower spec limit and an upper spec limit. And in this case, we'll look at characteristics of our design related to each one of the criteria and do a multiple attribute value analysis to determine that is that attribute of an alternative close to the target, is it close to the spec limits, and then perform an evaluation based on its closeness to what we would see as the preferred value, the target, a minimum, a maximum, something of this type. So in reviewing these techniques, we can see that basically preliminary type subject matter expert type knowledge could be used for the Pugh Matrix. We need technical nominal data for the TOPSIS method, and then for the SDI method we need technical data, quantitative data combined with specifications in order to perform the evaluation. So let's go look at a specific example using each one of these three techniques. Let's say that we have our design problem is to select a light bulb that will be used for a particular application. And we've identified 4 different alternative technologies that we could use for this lighting source. One being an incandescent bulb, a compact fluorescent, a light emitting diode, or a halogen type bulb. And the criteria, the characteristics we need to consider as part of our selection would be the light output, the power used by the device, the expected life, the unit cost, and then possibly a size attribute criteria, which we're going to use the cylindrical volume that's determined based on the maximum diameter and the maximum length of this particular component. And we've collected basic information besides just our subject matter knowledge about each of these technologies, lighting technologies. We have key parameter information for each one of these also. So the first thing we may do is let's take our criteria, which we've identified are the attributes of the bulbs that we're going to be evaluating them against, and such as light output, power used, life, unit cost, and this cylindrical volume, the size. And let's go do a AHP so that we can do a rank ordering. So let's say that we've gone through and we've done our pairwise comparisons and determined that is a particular option much more important, equal to, less important, or much less important than another characteristic. And then after completing this, each of the pairwise comparisons, we have established a scaled importance of these criteria. So what we've determined is that as we evaluate the technologies, we will consider light output to be the most important, followed by power used. Next will be the life. Next will be the unit cost, and then finally, of the lower importance, will be the actual size or the volume of this particular device. So we've established our scaled importance for our key criteria for this evaluation. Now the first technique we're going to use is the Pugh method. So in the Triptych tools, we'll go to the toolbars for the Triptych tools. One thing we can do is we can go take the information that's in the AHP and export this to a design selection technique. So let's use the copy worksheet function in the toolbar, and let's go move this information into a Pugh matrix. Okay, so let me do this as an example. And we see that our criteria information has been moved into a Pugh matrix type template along with the importance information, And now we can go and add additional options that we would put in here. So it may be that our first option is going to be the incandescent bulb. Our next option may be the compact fluorescent, and then the LED, and then the halogen lighting technology. All right. Now what we would do in the Pugh method is we would go and take a given option and compare it to the datum. And in this case, in terms of light output, let's say that a compact fluorescent of an equivalent design would have the same light output as an incandescent bulb. However, we do know that the power used is going to be better. It's a lower power dissipation, so it's going to be better for the compact fluorescent as compared to the incandescent. The life we're going to expect to be better. The unit cost, unfortunately, is probably going to be worse. They're probably going to be more expensive. And the size, let's say that we expect it to be about the same. And we would perform these comparisons for each one of these options against the datum, or the incandescent bulb in this case. So if we would have completed this, let me go ahead and go to a work at Pugh Matrix that I've completed the evaluations, and this would be the completed result of doing all the comparisons. And what we see here, as compared to the datum, or the incandescent bulb, the compact fluorescent has a lot of characteristics which are better, some characteristics which are the same, and a few that are worse also. And what we see here is that basically the compact fluorescent and the light emitting diode both have a lot of strengths that favor them over the incandescent bulb, some strengths that are equal in terms of performance or value to the incandescent bulb, and we see that there are a couple of characteristics, or at least one characteristic, that's worse than the incandescent bulb. But for the halogen, we see that there are more things that are worse for it than there are for the others, or worse for it here with this score of 6 as compared to the others. So these scores are based on computing the same, better, or worse comparison weighted by the importances that were established here. Now the next step is in a Pugh matrix is that once you've done one evaluation and we've compared compact fluorescent to incandescent bulb, then the next step would be to take the compact fluorescent and make it the datum, and now compare all the other alternatives such as LED and halogen to now this new datum condition. So I've done this in another Pugh matrix, which also you can achieve this by using the export icon we used before, and we can go create the next Pugh datum using the selected option as the datum, and then reperform the evaluation, and this will automatically generate the next Pugh matrix for you. So looking at that next Pugh, where we've now made the compact fluorescent the datum condition, and the incandescent bulb was the prior datum, which is showed grayed here. Now then we see that the compact fluorescent has a lot of strengths over the incandescent, has a lot of things that are maybe very similar to the light emitting diode, and the compact fluorescent has a lot of areas which are much better than the halogen bulb also. So at this point in time in our evaluation, it looks like that among the 4 options, the compact fluorescent and the light emitting diode may be 2 preferred options that we may want to go evaluate further. So the next thing we can do is let's go create a next level evaluation using the TOPSIS technique. So once again, we can go to our AHP with our rank ordered importances. We can move this information into a TOPSIS matrix, and the TOPSIS matrix would allow us now to, for our 4 options, we'll repeat the evaluation for all 4 again. In this example, we can indicate the units for each of the criteria. We can indicate our options up here in this area, the same options we had before, and now we can enter technical data for each option with respect to each one of the criteria. So in order to determine which one is closest to the goal condition or the ideal condition, we have to identify our goals. And the goals for this may be that for light output, we want to maximize the light output. For power used, for efficiency, we want to minimize the power used. The life we'd want to maximize. The unit cost we would probably want to minimize. And the volume, let's say we want to minimize this. Okay, so let me show you a TOPSIS matrix where I've entered in all the data. Actually, and all the data came from original data that we had on a prior worksheet. So I took this information in this matrix and used this as our source nominals to perform the evaluation. So in our completed TOPSIS matrix, we've included the units for each criterion, the same importances that we downloaded or exported from our AHP. We've entered the nominal values for each option against the criterion, and then we have the goals that we've established before. Now what we see is that among the various data that's available for these options, the ideal solution would have the maximum light output, the minimum power, the maximum life, the minimum unit cost, and the minimum size. And the minimums or the max and mins from our data are the ones indicated in the positive ideal column. So this would be the maximum available illumination, the minimum power, and so forth for the others. And we see from this evaluation that the option with the largest score in this case is the light emitting diode approach. The second closest solution would be the compact fluorescent, followed by, then pretty close at the end, the incandescent bulb and the halogen technology. So, and now at this point, using technical information, we see that the light emitting diode may be the preferred approach, and then second may be the compact fluorescent. Okay. Now then, let's say that we had really established design specifications that we had to satisfy for each one of our criteria. And in this case, we can make use of the SDI technique to determine which design, which of these four options, is the closest to meeting our specifications. So perform this, we could go back to our AHP technique. We can export then the criterion importances to a SDI matrix. And in this case, our matrix allows us to enter lower spec limits for each criterion, a target value for each, and a lower spec limit, upper spec limit for each, and then along with the units for each one of these criteria. We can also then enter as many options as we prefer to do the evaluation. And now what we'll do is enter technical information very similar to what we did for the TOPSIS technique. But when we do our evaluation, it's not based on a min or a max necessarily, but what we're going to be evaluating is, say, a linear in-spec condition where we would get a linear degradation from the target out to the spec limits. We'll do a value scoring type approach using a linear in-spec, or we can do this based on a quadratic relationship in-spec, or strictly in or out of spec condition, or minimize or maximize, or a 1 minus the probability of non-compliance method, which would take into account uncertainty possibly in the manufacturing or the operational environment. So where uncertainties are involved, you can use the 1 minus PNC technique. So let me show you a brief example of using the SDI approach for our light bulb evaluation. And let me go to this pre-populated SDI matrix. So in this case, we've indicated that like for light output, we have a target of 900 lumens, an upper spec limit of 1000, and a lower spec limit of 800. For power used, we have an upper spec limit of 60 watts, but we're trying to achieve a target of 10 watts. For life and unit cost, we're going to decide that we want to maximize the life and minimize the unit cost. So in this case, for the maximize or minimize, a target and spec conditions are not required. And so then what we can do is enter all our information, establish our scoring method, which I picked different methods here that we can apply, and then the evaluation will be performed based on how close a particular value is to the ideal target, and where we would get the most value if the solution met the target, we would get the least value if it was at the spec limits. So in this case, that value is going to be weighted by the importances. The individual weighted results for each of our 5 criteria in this case are shown down below. And then if we sum these together, we will get the overall weighted score for each one of the options. And now what we see is against these criteria that really the compact fluorescent bulb most closely meets our specifications. And the light emitting diode is second, followed by the incandescent bulb, and then finally the halogen lighting technology. So in this case, we've compared the actual data along with our specifications that we specified for this design and determined then which approach meets these conditions. So this is a brief demonstration of how you would use each one of these techniques. So basically what we've seen is, once again, in simple Excel worksheets with a very simple interface using the Triptych toolbars and using the templates that can be modified and edited in your worksheets. You can add additional columns for more matrix. You can add additional rows for additional criteria if you'd like. The options for cell and font coloring and formatting are available. If you have backup information that you want to reference as part of your design selection, you can add comments and hyperlinks to individual cells. All of the results are computed automatically based on the technique that's being performed, either Pugh, TOPSIS, or the SDI method. And there are some basic checks to tell you whether you've left out some information in some key cells that would be needed. And you can also then flow information from these tools into your FMEA or into to other techniques or other methods within the SDI tools. And all the functions are accessible from the toolbars or from the right-click menus. So in summary, what we have done in this discussion is evaluated some design alternatives in order to identify the preferred solution against a set of criteria that it's important for us to meet for our stakeholders. And you can use these techniques in any part of your development process or products, systems, design for Six Sigma, whichever activities you may be involved in. And what we've seen is these techniques are very valuable for determining preferred technologies, maybe which design approach, which alternate architecture of a design may be preferred. You can use the technique for performing vendor evaluations, for procurement type activities, so a wide variety of applications for these qualitative and quantitative design selection methods. So I'd like to thank you for attending this tutorial session. If you have any questions, please contact me. I'd like to welcome you to take advantage of the SDI tools, download them from the stat-design.com website, evaluate them, and if you have questions concerning your applications, please contact me and I'd be glad to assist you. Thank you very much.